Hello students, welcome back to the internal forces, axial force, shear force, bending moment and twisting moment diagram. These are the examples of the shear force diagram and bending moment diagram we learn through the examples. First example is that a simply supported beam with a central concentrated load. I believe this is to be elaborated very well to you so that you get the procedure right. And then next example onwards, we can cut short the exploration. So this is a beam with a central load. Uh, so we can find out the reactions. So there is no horizontal force. So there is, although in the pin joint there will be a horizontal reaction and a vertical reaction possible. For this particular problem, there is no horizontal reaction. There is a vertical reaction. So what you can do, you can apply your sigma fx0, sigma fy0, sigma moment about a point 0, and you can find out the reaction. But it is evident in this particular problem that P will be divided equally onto both parts. And let us go ahead with that, P by 2 and P by 2 reactions on both sides. I hope you will be able to find out the reactions well in due course of time. So how to find out the shear forces and bending moment at sections? Let us consider sections at certain distance. Let us consider a section at a distance x1 from the left end. So section D. So at section D, I separate the two beams into parts, two parts. So now this part, reactive force P by 2 is working, and at the cross section, as per our sign convention, I am considering the right part of the section. So right down shear V1 should exist there, and a moment which is counterclockwise M1 should also exist at that section. With this V1, M1 and the P2, this part of the beam should be in equilibrium. And I have put the section at an arbitrary distance x1 from the support. So I can vary the x1 from 0 to L by 2 and then get the values of the bending moment and shear forces at any location I want along the longitudinal axis. Now let's examine how it looks like to the other part. So passing the section at D will divide the beam into two parts. One part we have considered, the next part is here. So an equal and opposite forces, if I have indicated it is right down, it is the left up shear which should be acting on the same cross section. But now the cross section is of the second part of the beam, and then M1 will be just clockwise, equal and opposite to this M1. So this part will be in equilibrium with V1 shear, M1 bending moment, P force, active force, and then P2 reactive force. It may immediately be coming to your mind that the left part something is missing probably, that your reaction reflects actually the existence of P. So nothing is missed. Now, if you consider this part and apply the equilibrium equations, I have not done that in this video, but if you apply the equilibrium equation, you will realize that, so sigma vertical forces, if you do sum of the vertical forces and upward positive, you will get P by 2 plus P by 2 minus V1 is equal to 0. So you will get V1 is equal to P by 2. And that is true for the entire length of L by 2 because x1 you can vary from 0 to L by 2. And how about moment? You take moment about this point. If you take moment about this point, you will get P by 2 into x working clockwise. If you take clockwise positive, so your equation, equilibrium equation, moment equilibrium equation about this point at D point is P by 2 into x1 minus M1 is equal to 0. So M1 is equal to P by 2 into x1. Now x1 can vary from 0 to L by 2. So if you do similar thing for the right part and write down the equilibrium equation involving M1, V1, P and P by 2, you will get the same. And in fact, you can tally and check that once you come to the point D, either from the left part or from the right part, you are getting the same value. That will ascertain, because of course it was the assumption of yours, so it has to be true, and it is true from the equilibrium also. You can similarly, if you suspect that the characteristic of the beam may change onto the right part, you can consider another section at a distance x2, and you can separate out the beam into this part and this part as it is from the left part to up to E and from E to the support. So you can consider the equilibrium of this part and equilibrium of this part for finding out what is the values of M2 V2 and M2 V2 here. Either you do for this from this part or this part, it will be the same. Now this extent of x2 will be from L by 2 to L from left side. You could have taken this x2 from the right part also, but for that, this sign convention, you have to be very careful. No harm for that. Now, coming again to drawing the shear force and diagram and bending moment diagram, or you can say that let us understand what do you mean by the shear force and the bending moment at a section. So you vary the x1 from the left hand from 0 to L by 2, and you understand, you can put your palm onto the beam, and as you expose gradually from the left part, you will see that till it reaches to the P force, you will always get P by 2, and this is up. And what you have assumed as a sign convention, left up is positive. So you have a positive shear on the beam due to the reaction. So I put it positive shear, left up. Now, once you cross it, the story changes because P by 2 left up, but P is more than that, in fact double. So it suppresses down. So ultimately, if you are here and you are still considering x1 extended beyond L by 2, you will get actually P by 2 minus P, so minus P by 2. That's what it is. But if you are in confusion, I will advise you, you select this section and you can easily see from P by 2, you have again left up, right down. So you have a right up, so you have a negative shear. So you have a negative shear here. You see, this is the shear force diagram. In fact, to draw the shear force diagram, you should draw the longitudinal axis X. You should have the unit. What is P by 2, what is P, what is 2P, 1.5P, everything, a scale, the vertical axis and the horizontal axis, and draw the diagram. In fact, it is not meaningful to join it vertically from here to here, but sometimes for easy of understanding, I may join that, but that is not correct, but I know it, but it is convenient to join so that you, in my videos or the class notes, you can see that this happened, that you are up to here and then you have come down to here. For that I join. But that is not true. Now for the bending moment, it is again, it is P by 2 into x1. So x1 is extending from 0 to L by 2. So at the most, it will be P by 2 into L by 2. So PL by 4. And it will go up and up. And for the left, this part you have, and if you consider the right part, M1, you will see that you are getting a positive value from the equation. And that is how it is a positive bending moment. Things change when you cross the beam after P, it reduces. If you are still in confusion, don't go from left crossing P. You come from right side and take this P by 2 reaction, and what you see, you have already actually agreed that your sign convention, if you consider the right part, it is the anticlockwise moment positive. P by 2 is creating an anticlockwise moment. Fine, it will be P by 2 into X. It will gradually actually be increased to PL by 4 again. So this diagram expresses the variation of bending moment along the length of the beam. And this diagram expresses the variation of the shear force along the length of the beam. This we call the shear force diagram, SFD, and bending moment diagram, BMD. BMD is usually drawn on the compression side of the beam. That you will realize later because we are not considering the deformations. I should not have told you, but you will see repeatedly, and some students will ask that why can't I draw the diagram downward? Yes, you can. There is no harm. But usually we follow a norm where we draw it on the upper side, and upper side is compression while the beam is actually suppressed by the P force. It will bend downwards and its top will be in compression. We will draw the diagram over that, and that's the convention we follow. So I think this is the first example. So in examination, you have to reproduce such kind of diagrams, shear force diagram and bending moment diagram with sign convention agreed, and draw also the values. And sometimes we'll be asking you to determine the highest values or where it crosses the 0 point. You can observe a few things, that the shear force is constant. There is no change in the shear force, and the slope of the bending moment diagram is also constant. And then it is constant but negative. the slope also comes down. That we'll see later. And also, you can realize that as if the P force, if you add the shear force magnitude, P by 2 and P by 2, you get the force acting at that point. So similar things we'll observe further, but right now, let us stop it here and we will explore further with new examples.